Welcome everybody, my name is Verena Wolf, I'm from the Paderborn University and together with my colleague Sven Weinzel from the Friedrich-Alexander University in Erlangen-Nuremberg, we would like to present in this video our article Detecting Workarounds in Business Processes, a deep learning method for analyzing event logs. This article is presented in a session Business Process Analytics at the European Conference on Information Systems. So business processes that are performed in organizations often deviate from the described abstract process models issued by designers. These deviations are called workarounds, which play an important role for identifying and restructuring inefficient, dysfunctional, or obsolete processes. However, their detection is still difficult and they still remain undetected. So therefore, we designed a deep learning method for detecting workarounds in business processes automatically. So here you can see the agenda for this short video. First of all, we would like to talk about our motivation, then about the theoretical background, the research method that we applied, the artifact that we designed, then the evaluation that we performed, and finally the conclusion and future work. So aligning information systems and business processes is quite challenging because processes frequently change, for example, if a new digital technology is adopted. This can lead to the emergence of workarounds. A workaround is described as any adaptation of the work activities that is not expected or not specified to be changed in this manner. Workarounds can disrupt the efficiency and also the quality of business processes. And if they remain undetected, they may become institutionalized in the organization. And then they are hard to change again. At the same time, workarounds can also lead to a higher performance and thus they provide the great opportunity for analyzing and redesigning business processes. So far, existing manual detection methods like interviews or ethnographies they assume the awareness of workarounds and the willingness to expose the deviation by the interview partners. Further, they are quite labor-intense to identify workarounds on a large scale. On the other hand, there exist process mining methods in the BPM literature, but they are designed to detect anomalies in event log data, and they also have limited predictive quality in detecting workarounds automatically. Therefore, we set out to design a new method for detecting workarounds automatically, which is based on analyzing real-life event log data. Therefore, we apply deep neural networks to detect workarounds in high-dimensional data through multi-representation learning. So let's talk a little bit more about workarounds. The concept of workarounds is not fundamentally new. It already emerged in the mid-1980s to describe the apparent mismatch between work requirements and the design. Workarounds are omnipresent in almost every organization, and they frequently occur when employees have to use information systems to perform their day-to-day work. There are various reasons why workarounds emerge. For example, employees want to do some troubleshooting, they may want to avoid some rules or limitations, they might want to mitigate some poor information systems design, or they simply want to cut time. Workarounds can be directed either towards the information system or towards the business process. If they are directed towards the information systems, they may be manifested in injured responsibility or manipulated data. On the other hand, if they are directed toward processes, employees may want to repeat some activities or substitute activities or interchange activities. They may want to partially bystep some process steps or they want to add some activities. Our research follows the design science research paradigm for information systems as proposed by Hefner et al. And Gregor and Hefner. In line with the paradigm, we address and solve a real-world problem by designing a socio-technical artifact and generating new knowledge. We position our contribution as acceptation, as proposed by Gregor and Hefner, by adopting a deep learning-based method from business process management to a new problem context for identifying workarounds in event logs. After defining the problem, we identify 7 types of workarounds from the literature, as you just heard. Subsequently, we begin with the design cycle in which we develop our method for workaround detection based on deep learning in a way that allows us for detecting all 7 classes of workarounds in event log data. By rooting our work in the existing theoretical foundations and the methodologies, we ensure rigor and relevance. Then the artifact is instantiated, evaluated, and demonstrated. So we designed a deep learning-based method for detecting workarounds. The method detects automatically for each process instance of a real-life event log if a workaround of a particular type is included or not. The method comprises 5 phases, which you can see here. First, an initial vector-oriented dataset is created, which is based on an event log in order to apply deep neural networks. In the second phase, existing noisy data are removed from the dataset by using an autoencoder, which is a specific type of a deep neural network. In the third phase, workaround variations from a defined set of workaround types are randomly added to the existing process instances that are contained in the dataset. In this next phase, a classifier is learned by using a convolutional neural network. The classifier shall map the process instance to a workaround class. Finally, the learned classifier is applied on a left-out subset of the initial dataset, in which noisy data has not been removed. And how this exactly works will be explained by my colleague Sven.
Hello, my name is Sven Weinziel. Our method gets as input an event log, for example L1. L1 consists of 3 process instances. Each process instance includes events. In this example, an event is described by an activity, resource, and document type. The main purpose of this step is to transform an event log into a fixed-size vector-oriented dataset. Since deep neural networks, as used in this paper, require such a representation of data for computation. In the second step, the noise is removed from the dataset. For that, we use a deep neural network called autoencoder to calculate a reconstruction error for each process instance. So, if the reconstruction error of a process instance is lower or equal to t is a threshold, it is included to the dataset. Otherwise, it is excluded. We determine t as the median of all errors plus the standard deviation of all errors. In the first step, we add workarounds to 30% of the process instances of the dataset. The 30% are randomly selected. Each of the process instances is manipulated according to a workaround type. The workaround type is randomly selected. Additionally, a workaround type is represented by a set of rules enriched by random elements. In the example, the first process instance is not manipulated. Thus, it does not include a workaround. In contrast, the second process instance is manipulated and it includes a workaround of the class bypassed activity. Further, a classifier learns the mapping from the process instances to the workaround classes. For that, we use a CNN, a convolutional neural network, another type of neural network. We select a CNN for 2 reasons. First, it can deal with one-dimensional sequential input data. Second, it typically provides the capability of sparse interactions, making filters smaller than the input. This capability is promising for detecting workarounds, since workarounds can only be described by a few data elements. Last, our method predicts for new data workarounds by using the CNN. For the first process instance, no workaround, represented by class 0, is predicted. For the second process instance, the workaround of the class violated responsibility is predicted, represented by the class 1. Further, we evaluate our method based on 3 event logs. Each event log has different characteristics. Here, the context attributes are important since some workaround types can only be detected with such an attribute. For example, the workaround type violated responsibility requires the attribute resource. If we compare the test results of the three logs, we can see that the BPI 2019 achieved the highest predictive quality. If we look at the different workaround classes for the BPI 2019 event log, most of the predictions are equal to the target values. Regarding the prediction results, we can show for the BPI 2019 event log that our method is able to detect each workaround class. To sum up, our method can detect workarounds with a high predictive quality in event logs of standardized processes with a lower number of variations, a higher number of training instances, and a higher number of different activities. That means event types. With the detection of workarounds, actions can be derived to counteract or leverage workarounds. In future work, someone can specify different workaround types more precisely, investigate the relationship between autoencoders and CNNs, or consider traditional machine learning algorithms or other deep learning algorithms for learning the mapping from the process instances to the workaround classes. Finally, we would like to thank the session chair for giving us the opportunity to present our research to the IS community.